let's jump right in. Welcome to this explainer. Today, we're diving headfirst into this seriously fascinating world of unsupervised machine learning. We're going to see exactly how machines manage to find hidden patterns without any human guidance. You can think of it kind of like giving a detective a massive pile of evidence, but completely withholding the case file. They just have to figure out the story entirely on their own.
Now, in traditional supervised learning, the model gets an answer key, right? It's explicitly told, hey, this is a cat, or this is a dog. But our crucial question today is a bit trickier. How do you evaluate success when the model is flying completely blind? Seriously, what happens when there are literally no labels to tell the algorithm if it's right or wrong?
Well, that brings us to unsupervised learning. Without that handy answer key, we have to build models that can evaluate their own quality based purely on the mathematical properties of the data itself. We're trusting the algorithm to find intrinsic structures, groupings, and distributions that we, as humans, might not even be able to perceive. For instance, imagine just throwing a massive spreadsheet of raw user behavior at an algorithm and boom, it finds out that your customers naturally group into 3 distinct buying habits. And it does this without anyone telling the machine what those habits are beforehand. That is the absolute magic of unsupervised learning.
So to pull this off, our Data Detectives toolkit is basically divided into 3 main phases. First up, estimating the data's shape. Second, the art of clustering. And third, reducing dimensions for clarity.
All right, let's start with phase 1, estimating the data's shape by modeling the probability density function.
This is where the machine tries to figure out the fundamental shape of the unknown probability distribution that our data was actually drawn from in the first place. We map out that shape using something called kernel density estimation. It's like a balancing act. We're searching for the optimal hyperparameter, usually called h, which basically controls how jagged or smooth our model is. If we set h way too low, well, we overfit and we end up with a highly jagged, spiky line that tracks the noise too closely. But if we set it too high, we underfit, smoothing everything out into a blurry, generalized mound. By mathematically minimizing the error between the real underlying shape and our model, we lock in on that perfect good fit.
Moving right along to phase 2, the art of clustering, which is all about finding the groups.
This is where our data detective groups the data points into categories, entirely without knowing what those groups represent in the real world. A foundational method here is the famous k-means algorithm. Conceptually, it's pretty neat. Imagine randomly placing geometric centers, we call them centroids, right into your data space. Iteration by iteration, those centroids mathematically shift their positions, constantly recentering themselves until they lock into stable, spherical groups of data. Honestly, it's a bit like watching a chaotic party naturally organize itself into distinct conversation circles.
The crucial point to understand is that this is a continuous mathematical loop. First, the algorithm places a predetermined number of k-centroids. Then, it assigns data to those centroids based on Euclidean distance, basically just whatever is physically closest. After that, it recomputes the new geometric centers of those newly formed groups, and it just repeats the entire process over and over until the assignments simply stop changing.
Now, k-means is great. It really is. But it has a pretty massive blind spot. What if your groups aren't perfect spheres? That's exactly where density-based algorithms like dbScan and hdbScan step in. Instead of forcing data into rigid circular clusters, they look for contiguous areas of high data density. This incredibly smart approach allows them to find clusters of completely arbitrary organic shapes. And best of all, they do it without making you blindly guess the number of groups up front.
Because think about it. If we do use a centroid-based algorithm like k-means, we hit a major rhetorical roadblock right out of the gate. How do you reliably choose k, the number of clusters, when you don't even know what you're looking for in the first place? Like, how do you know if your data has 3 groups, or 4, or 50?
This brings us to a really clever concept called prediction strength. Here's how it works. We split the dataset into a training set and a test set, and we cluster both of them independently. If our chosen number k is actually the correct number of distinct clusters in reality, then the test data and the training data will perfectly agree on those group boundaries. If k is wrong, though, the boundaries will completely contradict each other.
So instead of just eyeballing scatter plots and making an educated guess, we calculate how often data points consistently end up in the same group across our different tests. We're essentially building a co-membership matrix to find a prediction strength score. If that score stays above 0.8, bingo, we can confidently say we found a mathematically sound answer for exactly how many groups actually exist in the data.
Okay, moving on to our next concept, the EM algorithm breakdown, focusing on soft clustering with Gaussian mixture models.
So what happens when the data is a bit ambiguous? Sometimes a single data point might belong to multiple groups at once, nestled right there on the border. This is where the brilliant Gaussian mixture model, or GMM, comes into play. It uses the expectation maximization algorithm. Conceptually, it's a lot like k-means, but with a twist. It uses soft clustering. This means a data point doesn't just strictly belong to cluster A or cluster B. Instead, it belongs to multiple elliptical clusters simultaneously, but with varying probabilities. It calculates the statistical likelihood of each example, constantly updating its understanding of the data's variance to find the absolute best fit.
If you watch this build over 40 iterations, you'll see the algorithm smoothly optimizing its parameters. By iteration 40, those Gaussian curves are perfectly hugging the true underlying shape of the data. It's softly mapping the probabilities to match reality, subtly adjusting the size and orientation of those ellipses to capture the nuanced, real-world spread of each and every group.
And finally, we arrive at phase 3, reducing dimensions for clarity, simplifying the scene.
This is exactly where we simplify that massive pile of clues so human detectives can actually comprehend them. You see, real-world datasets can have millions of features. Those are dimensions our human brains physically cannot visualize since we completely max out at 3D. So dimensionality reduction algorithms step in to squish these millions of features down to just 2 or 3 dimensions. They strip out the noise, they remove the highly correlated redundancy, and they leave behind a super clean, interpretable model where we can actually spot the patterns.
A real classic way we do this is with principal component analysis, or PCA. The algorithm hunts down the specific direction in the data that has the highest variance, meaning the direction where the data is spread out the absolute most. Then it simply projects the data points directly onto that line. It's literally collapsing a 2-dimensional scatterplot down into a 1-dimensional line, but critically, without losing the main story of how that data is fundamentally distributed.
While PCA is a total classic, modern algorithms like UMAP take this whole concept to the next level. UMAP brilliantly maps incredibly high-dimensional relationships down to a space we can easily visualize. It pulls this off by minimizing a metric called cross-entropy. Now, that sounds complex, but it essentially just penalizes the mathematical model if it fails to ensure that the local, neighborly properties of the data in the complex space are perfectly preserved in the simple space. Basically, it guarantees that if 2 data points were close friends in a million dimensions, they stay close friends when reduced down to just 2 dimensions.
Well, we've definitely covered a lot of ground today. From finding shapes with density estimation, to identifying hidden groups with clustering, to stripping away the noise with dimensionality reduction. So I want to leave you with a thought. The next time you're feeling totally overwhelmed with unstructured information, ask yourself, how could you reduce your own dimensions to clearly focus on the signal cutting through the noise? Thank you so much for exploring the Data Detectives Toolkit with me today.